everyone. Welcome back to Learning at 11th Hour. Today, we're going to look at a very interesting concept about inductors and inductance. I'm going to explain this concept of inductance with the help of an analogy where I'll draw similarities between a turbine and an inductor. A turbine is a mechanical component that stores energy in a rotating mass. Similarly, an inductor can be thought of as an electrical component which stores energy in a magnetic field. Just as a turbine uses a rotating mass such as blades or a flywheel to store energy, an inductor uses a magnetic field to store energy. When a force such as steam or water rotates the blade of a turbine, it stores kinetic energy which can later be released maybe in the form of electricity. Similarly, when current flows through an inductor, it creates a magnetic field which stores energy, and when the current is turned off, the energy is released back into the circuit. In both the cases, the amount of energy that can be stored is proportional to the size of the component. For example, a larger turbine can store more energy in its rotating mass, and a larger inductor can store more energy in its magnetic field. Therefore, we can draw an analogy in this manner. The turbine is analogous to the inductor here. The flow of water through the turbine is nothing but similar to the flow of electrons through the inductor, which is nothing but the flow of current. And the kinetic energy due to the flow of water, which is stored in the blades, is analogous to the energy which is stored in the magnetic field of the inductor. Having said this, let us now dwell into the more electrical aspect of an inductor. The inductor is represented as a coil in this manner. So, this is the symbol of the inductor, and there's going to be current flowing through this coil. Actually, there is a magnetic material acting as the core of this inductor. So, whenever current flows through these coils, there is a magnetic field which is induced around the inductor. If the value of this current goes up, then the amount of magnetic field or the magnetic field intensity around the inductor also goes up. And if the current decreases, the magnetic field weakens. Now, say if I change the direction of the current itself. So, instead of the direction being in this manner, if I make the direction in this manner. So, if this is my I now, then it causes a change in the magnetic field. In that case, a phenomenon called as electromagnetic induction happens over here, where an EMF is going to be generated. An EMF is nothing but an electromotive force. Now, this electromotive force causes a current to be induced. This current is not the same current as I, which now I have changed. This is the current which is induced by the electromotive force. Let me call it as I dashed. This I dashed, or the current induced by this EMF, is going to oppose this I. So it is going to be in the opposite direction like that. So I'll call it as I dashed. Now, because of this, it does not allow the magnetic field to change so easily. So this phenomenon is actually called as the Lenz's law. And this is the reason why the inductor does not allow the direction of current to be changed. But once it happens and the current direction is stabilized, it begins to act like a short circuit. To understand this scenario a little better, let's go back to our analogy with the turbine. So, say the turbine was rotating in the clockwise direction because the water was in this direction as shown. But now I want the direction of the turbine to change, and it changes because I have changed the direction of water like that. So, if this is the direction of water now, the turbine will have to start rotating in the anti clockwise direction. But will that happen immediately? No. So suppose I suddenly change the direction of water, this turbine will begin to slow down its speed of rotation, come to a standstill, and then it will start rotating in the opposite direction. In the same way, if I have an inductor with a current flowing in one particular direction, then it will take some time for the inductor to begin conducting current in the opposite direction. So, we say that the inductor does not easily allow for the change in direction of current. Let us view this with the help of a virtual simulation. So, this is the PHET simulation environment where I have taken three components here. One is the battery, one is the inductor, and another one is the switch. Now, this battery's voltage can be varied. So, let me keep it at say 10 volts, and I can change the inductance. So, if you observe the inductance value here, here it is 3.4. You can change the slider value and change the value of inductance. So if you notice, as the inductance increases, the number of coils goes up. The units of inductance is Henry. So if I have 4.2 Henries, these are the number of turns of coils. If I increase the inductance value to 8.2, the number of coils has gone up. If I take it totally down, there are just about 4 or 5. So let me just set it at say 4 Henries. Now this is a switch. I'm going to make a connection here between the switch and the battery and see how the current flows. So this is the first wire. This is the second wire which I'm going to connect. And this is the next one. Now, when I close the switch, let's see what happens. So there is a flow of current. If you notice, the flow of these blue lines, minus symbols, these are actually electrons. So the flow of current is starting in a slow way and picks up speed. This is because as the as the inductor stabilizes at a particular current, it tends to act like a short circuit. So let me change the direction of the battery now. See, the current flow completely stops and then it happens to change the direction. Let's observe it one more time. I've changed the direction of the battery again. So the terminals are switched. So it stops and then changes the direction. If I don't do anything, if I just let the current to flow, since it acts like a short circuit, it's like as if we've shorted the positive and negative terminal of the battery. So therefore, there's short circuit current flowing through it, and that's why it shows that the battery is burning. So let me open this switch. So that is the case of an ideal inductor, where we consider that the coils have no resistance. But that's not the real scenario. So in reality, there is going to be some resistance associated with the coils. So if I can include a resistor in the circuit and then perform the same simulation. So here we see that even over a period of time, the battery is not going to burn. That's because it ensures that the two terminals of the batteries are not directly shorted with each other. However, if I change the direction of the battery, we can still see that the current stops and then changes the direction of flow. That's because of the property of the inductor. From this, we can infer that if there is an inductor with a value of L henries and there is a current I flowing through it, then the voltage drop VL across the inductor can be given as L into the rate of change of current di by dt. And the power will be given as V into I, where V you can replace it with this value. So we get L d I square by dt, which is nothing but half L into I square. Now we can draw the energy relationship from this too. So we can say that the energy, say W, is integration of the power over time from say time t1 to t2. So that is nothing but half L I square dt integrated from T1 to T2. So this, for the time T1, the current would maybe say I1, and for T2 it would be I2. So we can say that the energy becomes half L I1 I2 square minus I1 square, or simply call it as half L I square. So the energy which is stored in the inductor is given by half Li square, and the voltage drop across the inductor is given by VL is equal to L di by dt. So that's all with today's video. So I hope the concept of inductor and inductance is clear to you all. This will be useful for you all when you go for analyzing AC circuits and also transient circuits. Please do subscribe to my channel and keep watching videos on circuit theory. Thank you.